I was contacted quite recently by Keith Hunter, who wrote to me because we'd mentioned Keith in the interviews that we did with Peter Woodhead about the what Peter thinks is the mechanism behind Earth expansion. And I'd looked at the Earth expansion stuff a few years ago and come across the work of Dr. James Maxlow, who's an Australian geologist. And people can look at that research separately. James Maxlow did what I thought was a very good presentation in 2005, where he covers all the main points. And then, as I said, Peter got in touch with me a couple of years ago, Peter Woodhead, up in Lancashire. We recorded these videos about what Peter thought was causing the Earth to expand. And one of the people that we mentioned was Keith, who's with me today and is spending some time. So thanks very much for that, Keith. And I just thought that I'd start off and ask Keith a little bit about the background to what his background is and how he sort of became interested in contacting me and so forth.
Well, it's good to be here. And basically, I mean, my own research interest in you might call the esoteric or the alternative theories began round about the late 90s. I've always been a fan of the X-Files, I might add. But
okay.
I was also interested, had quite an interest before then in Greek mythology and all the tales like in the Iliad by Homer and the Odyssey. And the idea that they were essentially all related to the stars, the planets, the gods, such as Zeus. Zeus is Jupiter. You've got Venus, Aphrodite, Ares, Mars. And I was also intrigued by the whole notion that a lot of these mythological stories were also really a narrative of celestial patterns, conjunctions, and also grand disasters solar system wide. So I wanted to look into that area. And one of the most interesting aspects of this were certain leading Egyptian myths, such as related to the whole theory of an ideal Earth-Moon system, some kind of a very harmonious ideal solar system that once existed many years ago. And this is based upon our units of angular measure of degrees, minutes, and seconds of arc. So I've got a diagram. Yeah.
So that was your area of interest. So it was kind of looking at some of the mythology and looking at a basis in the sort of configuration of the solar system, what it might have been, or in terms of how that was encoded in various myths. Is that the sort of thing that you're looking at?
Basically it. Yeah. It's particular. There's an Egyptian myth that said that the Earth once had 360 days per year.
Okay.
And the moon had a 30-day synodic month, and the Egyptians had this calendar system to that effect. And the extra 5 days on the end of a year, they deemed them to be unlucky. And they had this whole story about how it seemingly happened, that the Earth actually got these extra days. And it's a really intriguing tale. And basically, just to summarize it briefly, you had two deities, Nut, a sky goddess, and Geb, the earth goddess, and they're lovers. And Ra, the sun god, heard a prophecy that the offspring of Nut would depose him. So he cursed the earth and said Nut could not give birth on any day of the year, and there were 360 days. So this wisdom god, Thoth, he goes to see the moon god, Chonsu, and they play a game of drafts. And oddly enough, the stakes are that if Thoth wins, he will win a part of the moon's light. And he does win. And so he gains a part of the moon's light and transfers it to the earth, gives it to Nut. And this has the effect of making the moon weaker. So it becomes smaller in the sky. And instead of being able to shine its light all the time, it has to go through these phases, like phases we have now, full moon through to new moon. So it becomes diminished. And this increases the days by an extra 5 days. And Nut can give birth to her children. And they're all named 5 extra deities named after these extra days. And so I basically thought, is there any reality to this? Okay. And so I started to study all of the different things within the solar system. So for example, we've got 365.2421897 as a day. Yeah, that's how many days there are in a year. If you divide that by 360,
Yep.
you've got a ratio of change. You look at the moon, it's not 30 days, it's just about 29.53. I looked at the ratios there. If you also divide distance between the centre of the Earth and the centre of the moon by the Earth's radius, it's very close to 60, but it's about 60.29. So when you study the solar system, you realise everything's just slightly out of sync. And I was looking, is there a way to look at all these ratios of change and unify them and prove that you could back transform the system to an unusual, if you will, state of harmony?
Extrapolate backwards. And
the key to this actually came from a man called Johannes Kepler.
Oh, yes, Kepler's laws. Because I mean, we'll just dwell on that then for a minute, because before we sort of drive into more detail. So what you're basically doing right there is you're looking at the orbital period of objects in the solar system, bodies in the solar system, perhaps I should say, and you're looking at their orbital period, and you're working out the ratios of those. That's one factor of what you're doing, and so we're then going to see if we can extrapolate that backwards to give these ratios a more, come up with like figures of 60 rather than 60.2 and that sort of thing. And that's basically what you're looking at initially
and
here.
Just for the viewers who might not know what this means, I've got a little example on image 1. We can put that on,
Yep.
And basically, this is based upon the orbits of the Earth and Mars around the Sun, right? So you've got the orbital period, and these values here are taken from a pretty impeccable source, US Naval Observatory. I get the values from really exacting sources. And so you've got the orbital period, and you've got the mean distance. You see, all the planets, they don't have circular orbits. They're all slightly squashed. They're all elliptical. So they've got a mean distance and a closest point of approach and a furthest point. This law that Kepler found, that I'm going to discuss here, and Kepler, by the way, he lived 1571 to 1630, and he's a kind of a rock star, if you will, in the field of astronomy. He's one of the titans, if you will. All the astronomy stuff out there is based upon his initial views of elliptical orbits rather than circular ones. So what we've got here then, the first line, all I've done is I've divided the orbital period of Mars in days of 24 hours divided by the Earth's orbital period, and you get a ratio 1.88075. And I've done exactly the same thing with the mean distances between the planets, 1.51 whatever. Now you've got these two ratios of change for these two specific variables. One is time taken to orbit, the other one is mean distance. And all you do, this is what Kepler found, if you basically raise each ratio to a certain power, that's just the number of times you multiply it by itself, then you will equate the two variables. So in this case, it turns out that if you multiply the ratio of the orbital period by itself twice, you get the 3.537. And if you multiply the change in the mean distance by itself 3 times, you get the same ratio. And what basically this lawfully means is that, let's say we had the Earth and we didn't even know anything about Mars. We didn't know anything. We just had the Earth, we knew its orbital period, we knew its distance around the Sun. If I just speculated to myself, well, let's say I wanted to move the Earth's orbital distance to 1.5 times, which would be the same as Mars, but say Mars doesn't exist, If you have these three variables, the Earth's original, the distance you want to move it to, you ask yourself, what will be the new orbital period? Well, all you do is you basically use this law here as expressed. You will do the ratio of change, and you will use this cube root to work out where it is. So you basically just manipulate that law at the bottom slightly in order to work out what the orbital period of Mars would be, and it would turn out to be, the orbital period of the new Earth orbit would be, and it would turn out to be 686. So basically it's saying if you transform one thing, orbital period, it lawfully means that you will have to transform another variable associated with it to another level. So this was the principle, and all I basically did was I looked at these ratios between the little discrepancies in the Earth-Moon system, from 360 to its present day, from 30 moon month to its present day. I looked at these ratios, and all I did was if I could get one of the ratios, multiply it by itself a whole number of times, which is what a power is, and I found that they will connect to one another with different combinations of powers. Kepler uses 2 and 3. I found that different combinations of powers will reveal the answers. And these are low-level powers. It's not like, the really high powers. Because to be honest with you, you could prove anything working with extremely high powers. You could make it fit. But to get the accurate connections with low combinations, it is an astounding feat, and the error rates on these connections are so low you cannot ignore them. So I'll go through, if I will, the connection then, which led me, because what you've got to realise about Earth orbits, planetary orbits around the sun, they are elliptical in nature, right? Slightly squashed circle. Well, the geometry of planetary forms is also the same basis. If you get an ellipse of an elliptical orbit and you just rotate it around, you will get the same oblate spheroid as a planetary form. And so I found that you can get connections between components in a planet's orbit to physical components in a planet's form.
So if I can stop you right there then, because the term for the amount that an orbital is elliptical is called the eccentricity, isn't it? So in other words, what you're saying is, and the term for how much a planet is spherical is called the oblateness, isn't it?
Yeah. So, there's a formula for working it out, or flattening. They usually use flattening when they talk about planets.
Oh, flattening, Sorry, so in other words, you're saying there's a relationship for a given planet or a given body in the solar system. There is a relationship that you've found between the flattening and the eccentricity. Have I understood you correctly?
Well, basically the geometry is the same, and let's say you've got a component of an elliptical orbit. The mean distance is the semi-major axis.
Yep.
Well, the equatorial radius of a physical planet is the equivalent component. It is the semi-major axis. It's in an ellipse.
Yes.
So basically, I'm saying Kepler found that you can basically relate the semi-major axis of a planetary orbit to a change, say, in its orbital period. I found you can relate orbital periods to the semi-major axis of a planet's form. And so not only that, you can also the semi-minor axis. You see, the semi-major axis is equivalent to the equatorial radius. The semi-minor axis is the polar radius. And I found laws which connect these. And these allow me to actually, these bear directly on the issue of an Earth expansion, because I find that changes to the orbital period basically are tied into changes to the expansion of the planet through very exacting laws, just like Kepler's. So on screen here, then on image 3, I'll give an example of how this relates to the idea of an ideal Earth. And it says something special about imperial measures. So we've got the tropical year value at the top line. All I do is divide it by 360, and I get this ratio in bold, 1.01456, yeah? Now, we've got the equatorial radius. It says WGS 84, that's World Geodetic System 1984. This is our most advanced Earth ellipsoid model. And under that, we have the equatorial radius, which is equivalent to the semi-major axis component of the Earth form. It's given in kilometers, yeah? Now, again, that's practically from the cited book there, yeah? So all I've done, I've worked out the circumference, because the equatorial plane is circular. It's 2 times pi, so we get the circumference in kilometers. Now, what I have then done, here's the interesting part. I believe there's something very special about imperial measures based upon the foot and also the fathom being 6 feet, and also a unit measure of 6,000 feet. And this is evident from this particular equation. This is what suggests how the Earth itself has been transformed. So you can see I start out with the units for the circumference of the Earth in kilometers, just over 40,000. And I multiply it by this conversion ratio, 0.621371192. That is a conversion ratio, again, in the US Naval Observatory book, the precise conversion ratio to get kilometers to statute miles. Now, in statute miles, there's 5,280 feet. So I divide that by 6,000. That's the ratio to convert the circumference in kilometers to the circumference in units of precisely 6,000 British feet. And I call these ideal geographical miles. And the reason why I coined that term is because there is a unit measure called a geographical mile. and that is the equatorial circumference of the Earth split up into 21,600 parts. But that gives you a unit of about 6,087 feet. I'm basically saying there's something special about 6,000 feet units. So
another way, just to put something in there, because when you're talking about this, I think also of nautical miles, which is 1.1 of an ordinary mile, isn't it? I don't know if that's the same as a geographical mile.
No, it's slightly different.
But slightly different. But anyway, so just for the viewers and people that are listening, a regular mile that we measure on our cars when we drive around and stuff, that's I think 5,280. What is it? Feet. 280 feet, yeah. So this is the ideal geographical mile that you're talking about here. That's a bit bigger, isn't it? And it's is it a bit smaller than a nautical mile? I can't remember how big a
basically
mile.
I'm using a unit measure of precisely 6,000 British feet, right?
Okay.
A geographical mile and a nautical mile are both derived from the current ellipsoid shape of the Earth. The geographical mile is derived by saying, take the circumference of the Earth at the equator in feet and split it up by dividing it by 21,600, as an angular measure. And the arc length subtending each of those fractions is a unit of 6,087.25 feet. If you get because the Earth squashed down slightly, the pole circumference, which is elliptical, right? See, the equatorial circumference is circular, the polar circumference is elliptical. If you take the full polar circumference and divide by 21,600, you get the nautical mile, which is about 6,076 feet. There's a standard international definition of 6,076.11549, but what I'm using is not a nautical mile and not a standard geographical mile, 6,086 or 6,087 feet. I'm using a unit of precisely 6,000 feet. And the reason for that will become evident when you see the connections.
Clear.
So what I've basically got here then is the circumference of the Earth in these ideal geographical miles of 6,000 feet. And you can see is simply 21,913.2, right? And all I found was simply, if I take that and divide it by the ratio of change of the Earth tropical year, I get a value which is very, very close to 21,600 exactly. And I thought, well, this may well imply then that there's a real physical law here, just like with Kepler's law. As the Earth increases its orbital period, it will change its distance from the Sun. But here, as it increases its orbital period, it will simultaneously, in direct proportion, increase its equatorial circumference and by consequence its radius. And so what I've basically done is I've ended up reducing the circumference of the Earth by about 313 ideal geographical miles, and it's just over 1 geographical mile from getting this perfection. So it suggests there's something very special about unit measures, and this led me to believe that just as the Earth had an ideal year, 360 days, it also had a slightly shrunk ideal circumference, right? So it was slightly smaller in a real physical sense. And this led me on to basically look at the moon, because remember I said before, the distance between the center of the Earth and center of the moon divided by the Earth's own radius, it's very close to 60. So I'm thinking, well, ideally it should be 60. But if I've just shrunk the Earth,
so we're on slide. Just may stop you there. We're on slide number 4 now, with the calculations for the moon. I've got slide, and then just if again may interrupt you. Sorry to interrupt you. We'll go through this, but may I just ask about this idea of the Earth expansion? Did you always, were you always thinking that was there, or did you become aware of the Earth expansion, as you were doing this? Or in other words, basically, when did you become aware of the evidence for Earth expansion?
Well, it was with that connection there. I'd never really thought about the Earth, being of a different size. But with that connection there, it led me to think, based upon how Kepler had done his own laws, it made me think that yes, it's got an ideal orbit, it should have an ideal circumference. So that's what I basically thought about. And so this led me then to look at the refining of other ratios. And so if I've got then the circumference of the Earth as an ideal 21,600 British feet, say, all I do is multiply that by 60, and I've got what should be the ideal moon circumference, I believe is circular. And so what you see in this slide here then, image number 4, I've got ideal moon orbit is basically 60 times the ideal Earth circumference, which gives you this 1296000, which is actually the same units of seconds of arc in angular measure, right? But only here they're in not angular measures, but in units of 6,000 feet. So what I then did, the next bit is, I basically took the circumference of the Earth, circular, ideal, the circumference of the moon, circular, ideal, and I deduced the radius for them. Now usually you divide the circumference by 2 times pi, but a very peculiar feature here, I found that the rational fraction 22 divided by 7, which is very close to pi, yeah, it's 3.142 rather than 3.141, which is what pi begins. It's very slightly different, but this rational fraction appears physically to be tied into these laws, and pi for some reason fails. So I've got, as you can see in bold here, these two values for the radius of the moon orbit and the radius of the Earth. And again, I'm using a textbook value here for the mean Earth-Moon distance in kilometers. So it's 384,404 kilometers. Again, I convert that into units of 6,000 feet, right? And which gives me this 210,194 IGM, yeah? So you convert it there. And again, all I do now is I take that value and divide it by the ideal radius. So I've got this ratio. These are the two ratios in red here. The ratio of the change in the moon orbit from its ideal to its current in terms of its semi-major axis is this 1.0194, and then I've got, again, just repeated, the change of the Earth's orbital period. So I've got these two ratios, and the question, just like with Kepler's work, if I multiply these ratios by a whole number of times, raising them to a certain power, do they equate to one another? And the answer is yes, and with exceptional accuracy. And this goes on to image number 5. If you look at the top there, the very top line, I'm using a combination of powers 3 and 4. So all I've got is this 1.0194. That's the moon's semi-major axis change, this movement away from the Earth, yeah? All I do is cube it, and then reduce it to the 4th root. And the answer I get, as you can see there, is almost exact, which is exact to 6 places after the decimal point, very close to 7, to what is the change in the Earth's own orbital period just underneath it. You can see the one ends 7618, the other one ends 6380. What you get here then is a connection which is basically saying, going back to the Egyptian myth, what does the Egyptian myth say? It says the moon moves further away from the Earth, it gets smaller in the sky, and at the same time, the Earth increases its orbital period, its number of days. And this law here essentially proves that with exceptional precision, right? It basically is a real law saying, hey, at the same time as the Earth changes its orbital period, not only does it change its distance from the Sun, it changes equatorial radius by the same proportion, and the moon's radius also changes. And these laws prove that it back transforms to give you this 60-to-1 ratio between the Earth-Moon distance and radius of the Earth at the equator. Now, what I also want you to do, and this is what leads you to understand there's something special about ideal geographical miles of 6,000 feet. If you look at the bottom of this same image, look at the sequence of numbers in the current moon distance. I've already the decimal points, the current moon distance in ideal geographical miles, and then look at the ratio of change for the moon. The sequence is embedded in the ratio. Now, it's an interesting point because if you look at, say, Kepler's law and the way it works, you could use any arbitrary units of time and of distance in order for it to work, because it works based on ratios. But what you'll find is with these kinds of things here, I found that imperial measures are of a special universal set, and only with imperial measures do you get connections between ratios and the standalone values that compose those ratios. So you will see connections between things that you would never see if you were using arbitrary systems of measure. And that's what this example here shows, right? So
Right.
now here's the next bit.
Okay.
That law worked
Yeah, I
on
see what you're
powers
saying.
3 and 4, right? The same combination of powers can
4.
also connect the equatorial radius of the Earth to its polar radius. And this is image 6. Again, we start out with the Earth year and equatorial circumference ratio. It's the same one, right? And in this case, what I'm doing differently is, well, before when I was talking about the moon, I took that value and raised it to the 4th power and then reduced it to the 3rd root. Here, I do the reverse. I cube it, raise it to the 3rd power, and then reduce it to the 4th root, which makes it slightly less than before. Not making it great, it makes it less. And if I then use the current polar radius, again, a textbook value in kilometers, I convert it to units of 6,000 feet, and I simply divide by. I now get a value, this 3438, which is very, very close to the ideal radius of the Earth. And what this means, basically, is that the Earth must have been a perfect sphere when it had 360 days per year, because the transformation of its equatorial radius is greater than the transformation of its polar radius. So as you back transform it, they unify, and the Earth becomes a perfect sphere when it has 360 days. Now, here's the other interesting part. The moon. The synodic month of the moon, it has currently, and this is where we're going on to image 7. Again, I'm starting up with the same ratio of change
7
for the Earth orbital period, which is the same as its physical equator. I'm now using powers 12 and 11. This, when you apply them in the law given, just raises up the ratio slightly. And if I take the current synodic moon month, 29.5305, now again, that's straight out of the US Naval Observatory book, and I multiply that ratio by it, I get practically dead on 30 days, right? And just to give you a margin of error thing here, the difference between 30 days and this 29.53 is just over 40,000 seconds of time by the watch, because it's just less than half a day, just under 40,000. The error rate on this connection here, with this law working, is about 0.3 of 1 second. That's how accurate this connection is, right? So, because it...
One of the things I've just noticed here as well in these examples that you've been showing, I think, the powers that you're using, they're 1 power apart, like you've got 4 and 3 and 3 and 4 and 2 and 3, and I think all the ones that you've shown me. So that's just an observation, really. You know, the powers that you're using in these, in these calculations are just one power apart.
There are other laws of proportion, which have a variety of different powers, and I'll just as you mentioned that, this is my own book, and I say that I don't just look at the Earth and the Moon. I look at all the planets in the solar system, and you can see a variety of different laws on many different powers. One of the points that I found was that when the Earth had 360 days per year, the whole solar system was in a state of unusual harmony. All the planets, they were all in these very special orbital periods, all very harmonious. The whole system has basically been disrupted and reconfigured in a new way. And so the laws you're just saying about that point about them being 1 power different, I've got many laws which are very different to that, just putting that in there. So,
okay, all right.
So what we've got here so far then, just to summarize the system, is we basically got a series of connections all based on laws of proportion of the same format as Johannes Kepler, but just using different combinations of powers. And they accurately connect up various components of the Earth and the Moon system, which back transform the system to an ideal harmonious state with a 60-to-1 ratio, with the Earth being a perfect sphere, the whole works, So this led me to believe that this is a very real system, right? A very real configuration. So once you've realized that, the next question is there any scientific evidence out there that backs this up? Because basically, if I'm saying the moon's increasing by a certain amount, moving away from the Earth, and that's tied into the Earth expanding, I'd want to find out in the literature, what's the rate of the moon moving? What's the rate of the Earth expansion? Is there anything, do my laws have validity? And this brings me on to slide number 8.
Yes.
And you can see that mean Earth movements, again, it's in kilometers. I'm using the metric system here because this is just for ratios. And a lot of these cited values for rates of change are in metric. So the moon happens to be moving away from the Earth at 37.8 millimeters per year. That's one of these very accurate values based upon bouncing, laser beams off the moon. That's a cited value in some research papers, and also James Maxwell cites that very value in his own book on Earth expansion. So that value there, then all I've done, as you can see, I add it to what is the standard value, for the current Earth, current moon semi-major axis. So I assume it's changed over 1 year by that value. And all I do the ratio between those, and I use my laws of proportion. I take it to the third power, reduce it to the fourth root, and in bold there, you've got this ratio of change, 1 point, and then there's 10 zeros, and then it's 7375. So basically, I'm saying if the moon is increasing by this 37.8, the ratio of change for the Earth's equatorial circumference is this 1.00 whatever 7375, and all I do is I multiply that ratio by the circumference of the radius of the Earth, and again it's converting to millimeters, and as you can see, all it does is it gives you an extra 0.47 millimeter increase, right? It's the same value but just with that extra. So in other words, I'm saying the increase in the equator of the Earth is 0.47 millimeters per year, right?
And basically you've derived that from the calculation and the observation that the moon is receding from the Earth at 37.8 millimeters per year. That's basically what the way you've done that.
So I'm just using the same laws of proportion, but just going back over 1 year and seeing what the expansion is. Now, I said that the Earth was a perfect sphere, so we've got the other variant law of proportion that I use to simply work out what the increase is of the polar radius, and that is 351 millimeters increase a year. So the average Earth expansion is 0.411 millimeters a year, right, according to my law. Now, then I'm going to say, in the literature, what are people saying about Earth expansion? What the scientists say. So here we go on to slide image number 9. This is from a pretty scholarly article on the internet, and I've got the link there as well. And this is where things get a bit interesting. We've got a guy called Carey, 1970, and it says he makes a bold suggestion of a rapid rate of increase of about 8 millimeters a year, right? So he's well over this 0.411. But then he goes on to say, almost universally, other authors and their calculations, they actually think it's 0.5 millimeters per year. So these guys here are effectively backing me up ballpark with what they're saying. Almost universally. But he and C. Carey has gone with a higher value. And this is an interesting divergence in what people are thinking about Earth expansion. So let's go on to image number 10. Now, this is a citation. This is all a quote from James Maxwell's book on the origin of continents and oceans. This is from page 2. See, I have a copy of his book. We exchanged books, you see. So I've got a copy of his book, And this is what he says. He refers to a more modern study done, 2011, and this is a 0.0 millimeters per year in recent decades increase, right? But James Maxwell, on the other hand, he's got a rate of expansion of about 22 millimeters per year, right? This is about 45 times bigger than my estimate, which is in line with what the other theorists are saying. And interestingly enough, I'll just tell you this. I have been interested in this Earth expansion rate, and I looked into this, and I have private correspondence that I did with some of the guys behind this very study, which gives 0.2, yeah. And I emailed them. This is over a year ago, and I dug out the email just yesterday. And I asked them about this, and they were telling me about the confidence rate of the study, and they were saying like that
Yes.
they needed it to be about 0.4 in order for them to be confident of Earth expansion, and they'd really have liked 0.6. Yeah. So what they were basically telling me with their margins of error is that it was right on the borderline of what they considered significant. So the value I'm going with, around about 0.411 as an average, they might not regard that as significant, even if they got it with their studies. It's just so borderline. But I do believe that I am right, that it is 0.41, that these laws are correct, and that they are very much in line with the conservative views of the people who are looking at this. It's just that it's so small that even their own studies, even if they did detect it, they'd still be wondering whether it's real or not. Yeah,
it's
exactly.
Just experimental noise.
But I do believe it's real, and I believe
yeah.
the earlier theorists who gave this 0.5, they were about right. Yeah, and Maxlow with his 22 millimeters is wrong, and I've got very specific reasons why I believe he's wrong with this. And in all fairness to Maxlow as well, in his book he gives a table. I think there's about 6 or 7 other theorists, and they're all giving values of like 20, 22, 24ish. They're all ballpark. But as it says in Maxlow's book here, he says, while this is encouraging, referring to his 0.2, he says it's well short of his 22 millimeters per year increase of the Earth radius based upon seafloor surface area data. Now, this is so critical, right? He's doing something very different here. It's an interpretation of the seafloor spreading data, which leads him to believe this very high value. And before I go on to explain the differences between my own ideas on the seafloor spreading data and Maxlow's, I just want to say something. This is a question that a lot of people may be interested in. I've just used my laws of proportion to go back, say, 1 year or so, and look at subtle changes to the system of the Earth and Moon. A lot of people have wanted, to know, and Peter Woodhead himself in one of the videos, he queried what was the time I thought this entire system existed in history, right? So I thought I'll just go on to explain when I believe this ideal system existed. And this is image 11.
Great.
And what you've got on screen, the top line, is the current Earth-Moon distance in ideal geographical miles of 6,000 feet. And I subtract from that what is the ideal distance. So I now get the difference. And again, I've converted this into inches. Yeah, so it's 6,000 times 12 times that, and then I've taken the speed of the moving away per year. It's 37.8 millimeters, or 3.78 centimeters. Conversion rate is 2.54 to inches. Simple division sum gives me a ballpark figure 194 million years ago, when the moon will have been its ideal orbit, and therefore all the other factors will have been ideal too. But that, of course, is assuming that this rate of change for the moon is a linear thing. You see, we've only got these accurate measures for like the past few years or so. So we haven't got a rate of change of the speed of movement away. So what I found was a brilliant study on the internet, a very scholarly study looking at the fossil record, which allowed me to derive a far better answer. And this is image 12. And if you're going to put a page on your website on this, I will give you the link, Sandro, to the study behind this, so you can put the links on.
That'd be great. Yes, if you could send me all the links, that'd be brilliant. Okay, go on, carry on.
What I've done is I've taken the data from this study and summarized it myself in a spreadsheet. And what this data looked at was the synodic month in the past, and what it's all based on is the fossils of life forms which are tied in effectively to celestial cycles. So you can ingeniously work out the actual length of the synodic month,
Oh wow! I didn't know it was possible.
Not even I did. I was amazed. It's all based upon what is it? let's see, a bivalve. It's bivalve fossil data. Basically, it's little life forms which have been fossilized going back, and the geologists basically have done very, very many samples in these various epochs. You can see like Pleistocene, Pliocene, and Jurassic, and all the rest of it. And so, admittedly, they've got some samples, large samples for some periods, and others they've only got like a few. Yeah. So, what I've done here in bold at the bottom of each column, I've put in the mean value. So I've added them all together and divided by the sample number, and that gives you the total values. And you can just see a kind of a steady trend that as you're going backwards in time, the synodic month was getting greater. So the best samples, actually, if you can see the first sample, 11,000 to 1.8 million years, it's a large sample, 29.33. Yeah, slightly less than the current observed month. Yeah, but if you then look at the Cretaceous period, again a large sample, 29.8, and then your Carboniferous one, another very large sample, 30.218. Those are definitely give you that real trend. But what I did then, I took this data, and you see how we've got the Pleistocene and all the others. They're all date ranges. What I did was I averaged the dates range. So I added them two together and divided by. So Pleistocene, 11,000 plus 1.8 million divided by 2. I did that to basically get a mean range, and I looked at the mean values, and this brings us to image 11. And this is a scatter graph plotted using Microsoft's Excel program. And you can see on the y-axis, we've got the synodic month itself, and on the x-axis, they're all in millions of years going backwards in time. Now, you can see the data looks pretty scattered. But in Excel, there is a magic button called trend line, okay? And when you press the button, the magic works. So these two lines here, these are lines of best fit. I didn't come up with these lines. I didn't make these up. These are directly created by just pressing the trend line button. It gives you different types of curves. And the ones I've given here, which I think are the most appropriate, if you will, is the linear curve, which is a line of best fit, assuming a constant rate, which I don't really believe, to be honest. It'd be very unlikely. And the other one is a polynomial curve, which is a mathematical curve. It's a certain special form of progressive mathematics. And again, it gives you these here. And what you get from this, I've marked on in red, according to the linear curve, if we were to go back in time, the synodic month would be 236 million years ago. And if it's the polynomial curve, it's about 270 million. And the average of those is about 253 million. So based upon the moon movement, it was about 194 million. And I believe that it is slightly curved. We would have this difference. So we've got a kind of a mean value of about 253 million, which seems to be the ballpark figure when this system would have, existed, the ideal. You see, you cannot separate the moon semi-major axis from the synodic month. They're components of one thing. So you'd have to defer the change in the semi-major axis to the synodic month, because we've got a trend line effectively with that data, which we don't have with the moon movement. So this makes me very confident that around about 250 million years ago, this is when this ideal system occurred. Now, before I just get on to talking about more detailed Earth expansion stuff, I want to talk about a little bit about some of what the implications are. In my system, and when I talk about an ideal Earth-Moon system, say existing 50 million years ago, I talk about the Earth having an ideal orbit of 360 days per year. The thing is, though, I do not believe the Earth was rotating on its axis 360 times to complete one orbit. I believe that is a pure orbital time. And the Earth itself, because it's a perfect sphere, it would not be rotating. It would be showing the same side to the sun, just as the moon today shows the same side to the Earth. Yeah? When a celestial body is rotating, that's when centrifugal forces kick in, expands at the equator, and slightly contracts, yeah? So that's what makes it an ellipsoid. My mathematics say it's a perfect sphere. It cannot be rotating. So this orbital ratio of change, even though we do now have the Earth rotating 24-hour days, yeah, when it was a perfect sphere, it was not rotating. And that has implications on mass distribution inside the Earth. So that's a point to note there, right? So the question is, what is it that sets the Earth in motion? Something must disrupt us, yeah, to get the Earth in motion. Yep. And bearing in mind, we've got this system, value here, really ballpark 200 million years, which brings me to issue number 14, if you could briefly bring that up, a book by Joseph Farrell called The Cosmic War. I've got a few of these guys. I was in a conference with him a few years ago, along with Richard Hoagland, and he basically is talking about the work of one Van Flandern, Thomas Van Flandern.
Tom Van Flandern, yeah, I'm familiar with him.
His book's called
I'm familiar with Joseph Farrell as well.
Yeah, Tom Van Flandern's book is Dark Matter, Missing Planets and New Comets.
Okay.
And he's developed a theory called the multiple exploded planet hypothesis, right? You see, we have in our solar system a few asteroid belts. We've got a debris field between Mars and Jupiter.
Yep.
And we've also got a debris field that begins at Neptune and goes further out beyond Pluto, called the Kuiper Belt.
Kuiper Belt, yep.
And basically, we've got evidence, that these are the debris fields of planets that have exploded. You can cite like the moon of Iapetus. It's on one side, it's got this black soot-like stain on it.
Yeah, I've done a whole article about Iapetus.
And you also will have known Mars is cratered to hell on one side and on the other. Yeah,
that's right.
So
that's right.
This again implies that we've had, explosions of planets there, and also that this is what's created some of the returning comets, and this is what Van Flandern talks about. Now, Van Flandern, in developing his theory, has looked into the geological record, right, for periods when he believes these major explosions occurred, and he cites them as bodies within the main asteroid belt primarily, 3 separate explosions of bodies located in the main asteroid belt between Mars and Jupiter. And he gives dates for them, and I'll just read out. He gives code numbers for these planets as well, and he associates them with layers of the Earth. So let me just read out. This is a citation here from Joseph Farrell citing Van Flandern. He said, numerous unusual geological anomalies associated with the K/T boundary layers on Earth closely match the predicted consequences of an exploded planet, especially their global nature. But the geological dating of that layer to approximately 65 million years ago, and an even more devastating event recorded in geological layers at 250 million years ago, do not well match the established dating of the most recent solar system explosion event at 3.2 million years ago. Basically, what he's saying is we've got these 3 massive events, 250 million, 65, and 3.2. And what he's talking about here with respect to this 3.2 million years ago is the comets, because just a few pages on, he then goes on to say, and again, this is quoting Van Flandern. He says, I thus tentatively associate the earlier larger mass extinction event at 250 million years ago with the explosion of a planet in the main asteroid belt he calls Planet K with iron meteorites because of their long cosmic ray exposure ranges. Then he goes on to say, and I tentatively associate the small event at 65 million years ago with the explosion of Planet V in the inner asteroid belt. Yeah, and again, and this is with the acrondrite and stony iron meteorites. Basically, he's looking at different meteorites within and deducing different planets blowing up. So he's got one at 250 million, the biggest one at 65 million. But then he goes on to say the event at 3.2 million years resulted in all the comets that survived to the present must have been an explosion of a much smaller body in the asteroid belt. So this point about the 3.2 million, he's targeting that one as being basically responsible for the comet. But clearly we've got him talking about large objects exploding. And I can also cite the work of another man called Ovenden. He, in the 1970s, he did some calculations to actually try to work out a mass value for the planet between Mars and Jupiter, or at least the biggest one. Now, just for scaling purposes, when we look at the planets and the ordering of the planets, we start out with small rocky-type planets. You know, we've got Mercury, Venus, Earth, and Mars. Then we've got the asteroid belt between Mars and Jupiter. And Jupiter begins the gas giant series. Jupiter's 318 Earth masses. Saturn is about 93 Earth masses. Uranus is about 14, and Neptune's about 17 Earth masses. They're all gas giants. So you might want to think, well, if the asteroid belt is between the gas giant series and the smaller one, you'd be thinking, would it be a large body or a small body? And there was an individual called Ovenden who he looked into this matter, and he did some calculations, and according to his calculations in the 1970s, the large body, which would be the largest body in the asteroid belt, he put it on par with the mass of Saturn at about 93 Earth masses. So he thought it was a very, very large body. Now, with Van Flanden's work here, he's talking about multiple exploded bodies. So you'd be thinking, well, this large body would have moons around it. And oddly enough, the debris field as it stands now, there is within it a planet called Ceres. Yes. And Ceres makes up 1/3 of the entire mass of the asteroid belt, yeah?
Yes.
And it is a small spherical type object, whereas the other major objects within the field are like jagged edge pieces of rock. So you can see Ceres must be a surviving moon of some sort.
That's what you think, isn't it? Yeah. Yeah. Those strange lights that they photographed, haven't we, and stuff recently, and so makes you wonder, doesn't it?
It does. So what we'd be thinking here is that we had a large gas giant type explode. This would be the 250 million year disaster, the biggest one, and possibly a series of smaller planets which may have been moons of that. One moon, Ceres, surviving. So this gives you these disaster bands, yes? But the thing is, these disasters, you can imagine, if a planet blows up, you're going to have a massive shock wave go throughout the solar system. And this is going to disrupt like hell the Earth, right? So as a result of that then, this goes on to explain my difference with the work of James Maxlow and others. And let's go to image number 15 here. This is the basically the image. This is an image that is in Maxlow's book, the title of which I cited previously. And you can see, staring right in the middle, he talks about a continental crustal rupture 250 million years ago.
How interesting,
which ties into Van Flanden's date, which also looking at the geological record, which he holds was an exploding planet, and it also ties in very nicely to the synodic month and the ideal Earth-Moon system existing right there. And so if we're looking for an event which initiates a big change in the Earth-Moon system, setting the Earth in rotation, causing it to expand, I would say this is the time, 250 million years ago. Everything's converging there. But then you can see from Maxlow's diagram here, right? Along the x-axis, he's got millions of years in time. Now, the Earth's standard Earth age is 4.5 billion years. So he only goes as far back as 2.5 billion in the diagram. You can see he thinks the Earth's been very constant in its size, going back a long way. What he then sees is the Earth start to expand, and the graph goes exponential. And what we have is, as you can see on the y-axis, the Earth radius in kilometers. Right at the top, we're just over 6,000, it's 6,378 kilometers is the current Earth radius, right? So what he sees then is the Earth expanding and expanding, and between about a billion years ago to about 250 million, the Earth is suffering an expansion, It is still suffering an expansion. And then there's this crustal rupture event, and it continues to expand at an even faster rate. And this is the graph that Maxlow's come up with, which is strongly tied into this 22 millimeter per year radius increase, because he thinks it's really, really, operating at those high levels.
Yes.
And this is based on the seafloor spreading data, right?
Okay, yeah.
Now, the issue I've got with the seafloor spreading data is the interpretation of it.
Okay.
Because Maxlow's entire theory, it hangs upon a very special interpretation of that data. And it's nothing to do with disputing the ages of the bands. I don't dispute those at all. It's an interpretation of what it means. So, just to summarize Maxlow's theories, and how they differ from my own. In fact, I'll tell you how my own theories work out first, right? I believe that 250 million years ago, when the Earth was in its ideal system, right, it was slightly less in its size. These laws of proportion I've got basically would say it's only about 57 miles less in its radius, right?
Okay.
Maxwell's view, according to his own description here, 250 million years ago, he holds it to be about 2,000 miles less in its radius, approximately half the size. Now, I disagree with that completely, but he holds it to be that, right? I hold it to be only slightly different. So for me, I do believe in a Pangea, and all the continents were at one time locked together. But for me, I believe that occurred a few billion years ago. When we go back 250 million years ago, the continents were very close to where they are right now. Pangea has already been lost. And what I see, and I know that other theorists have looked at the issue of oceans, we may not have had oceans as such, but what I see is the continental landmass material, right, is on top of and at a higher level than a more inner layer which has been expanding and has cracked the continents and separated them, yeah? So I see that to be already well in place. Now, at that point, we may then have had no massive crustal disruptions. In other words, no fault lines or fissures, yeah? We've just got that set up like that, yeah? Now, what happens 250 million years ago then is boom, a planet blows up, a massive planet, a shock wave goes throughout the solar system. The Earth is hit, and this is what causes this crustal rupture. Now, to give a very important illustration of what I believe is going on here, right, Maxwell holds to the view that we have material coming through the cracks of the crustal rupture. And if you go to image number 16, you'll see what I'm talking about.
Okay.
He holds that we've got this seafloor spreading, right? Because when he looked at the landmass continents, right, the land masses, we know the Earth's about 4.5 billion years, that's the standard view. But when they looked at all the ages of all the material underneath the oceans, underneath the sea floor, none of it was dated to beyond 280 million years ago. And you can see this diagram only goes with the labeling to the Jurassic period, but you can see these bands.
Yes, yeah, I'm familiar with this. Yeah.
The quaternary bands, you know, the bright or lightish pink one, these are the mid-ocean ridge type things, and you can see a series of bands coming off it with kind of cut-off points, yeah? And the bands get kind of thicker in many ways as you go away from them. Some of the early ones, like the yellow one, for example, a bit thicker than the like deeper, what's that word, like lightish brownish, dirty kind of orange, yeah? You can see that, but then you look at some of these other ones, like the green ones, and a lot bigger in areas than the red ones from the Pleistocene, yeah? So you've got this pattern here. Okay. So again, now just to give you an indication, let's go on to image 17. This is perhaps a better one.
Yep.
This is a more fluid thing, and you've got 0 to 280 million. You can see some of the stuff in the Mediterranean is the 28 million, yeah? Yes. But you've got all the mid-ocean ridges, and you've got these bands as you can see them, yeah? Now, how are these bands formed then, right? And the key word really is bands. Well, when this shock wave from this planet, multiple planets have blown up, the shock wave, say 250 million years ago, right? It hits the Earth. What does it do? Well, I envisage the Earth, its continents are well separated. There's Saturn of a layer underneath them, if you will, which is of a obviously lesser thickness. It's underneath them, yeah? This is the layer that ruptures and all the fault lines and the cracks appear, you know, in what is now underneath the ocean, these mid-ocean ridges, yeah? So imagine then, my fingers touching here, right? From my knuckles to here is the underneath the ocean bit, the seafloor bit, if you will, a shell, an inner shell. My knuckles going across here and here, the continental landmass is slightly higher, yeah? Imagine when my fingers touch along there, yeah? We have a shock wave hit the Earth. What happens? The plates might jostle they crack, a gap appears, material comes up, flows right over, right up to the continents. They stabilize. The material solidifies, its age is geologically fixed, yeah? Then we go a bit further on in time. What happens? More shock waves hit the Earth. What happens? Again, the plates jostle. A crack, material comes in, flows over, but not as much as before.
Okay.
It stabilizes. Now we've got one band here, that could be like 250 million years, another band here, which is over the top of it, lapping it, yeah? About 65 million, yeah? And then that repeats, and it keeps on doing it with these shock waves at periodic times every couple of tens of millions of years, yeah? And you get material flowing over, yeah? And I think that the seafloor spreading data is evidence of periodic shocks to the Earth, causing a rupture and disruption of the plates and material to come through the gaps and flow over. And effectively, the bands are evidence of, in effect, the strength of the disruption, yeah?
Yes.
At a particular time, yeah? And the ages of the bands date these catastrophes, yeah?
Okay.
Now, that is how I believe it works. Now, why does Mach's law differ? Well, if you go online and you see his presentations, or you see what he's saying, his interpretation of the seafloor spreading data is very different.
Yes.
You see, whereas I said I believe that 250 million years ago, we've got the continents well separated, we've got them on top of a lower level layer, if you will, and it's that lower level layer that's cracked,
Yes.
which is now the bottom of the seafloor. Yes. What Mach's law does is, going back to his diagram image 15, he thinks that Pangaea was around about 250 million years ago. The Earth was about half its size, all the continents were together.
Okay.
And then this crustal rupture event occurs, right? And the cracks appear in the continental material. Now, to give you an example, this is what Mach's law thinks. Imagine my fingers then are the continents, right? The whole here is all continents, all continents, not seafloor bit, not like in my example. The whole's continents, yeah? And you've got these little cracks appear all over the place. So what he thinks occurs from interpreting his data is this. This crustal rupture occurs. A gap appears. And he sees this as, in his graph, the Earth is expanding and expanding and expanding and keeping together until it reaches a kind of a critical point of expansion and then crack. The continental plates crack and a gap appears. And Mach's law then says material comes up, fills in the gap, but does not flow over. Does not flow over, fills in the gap only. So as the gap gets bigger and bigger, more materials coming in and spreading out, filling in, and it's filling in here, filling in the gaps. Critical, filling in the gaps.
Okay.
Because if you fill in the gaps all around the network, you will have the circumference of the Earth increase, and from that you'll be able to work out the radius increase because it's 2 pi. So if you...
That's what we've done,
Yeah, exactly. But here's the problem. It all hinges upon the interpretation that the seafloor spreading fills in the gaps. If the material spills out and violently flows over, Mach's law is dead in the water. The entire seafloor spreading theory is it's gone. It's up in smoke. Because you cannot derive a value for the Earth expansion, right, unless you hold to the view that you're purely filling in the gaps.
Sure, So in other words, I appreciate what you're saying, and that is that Mach's law is assuming that all of the seafloor, that's the age of it, basically dictates how much new seafloor has been created, and that in of itself dictates how much the Earth has expanded. But what you're essentially saying is that there's not necessarily a direct relationship there, because the amount that's spread apart, there may be bits that have overlapped, and you don't know how much overlap there is in each sort of period of expansion or period of outflowing, whatever you want to call it, if you don't quite want to call it expansion. In other words, you could, by your way of explaining it, there could be an outflowing, but the outflowing just goes over the top and doesn't actually cause any pushing a part of the continent.
Exactly.
That's essentially what you're saying, isn't
Yeah.
it?
If the disruption occurs, and I believe it's due to planetary shock waves, if it occurs and material comes up and flows violently over right up to the edges of the continents, if that's the case, the entire rate of expansion that he's come up with is completely wrong.
From what you've said there, you've made me think of something in relation to that, which is if you need to also look at the height of the ocean floor and what the actual height of the material that's come out or flowed over or whatever it's done. So you need to do a volumetric calculation with that bit of the seafloor, and I thought of that where the actual rift has occurred, and you're going to get at least a little bit of ridges, some type of ridging, and you can see that on the flipping maps. So you need to take the volume of those ridges into account in terms of how much as the expansion has happened. So yeah, I can accept that.
Because I mean that for me is the major difference. I see once these cracks occur, say beginning 250 million, the material just spews out and flows over. But because the land continents are substantially higher, it doesn't flow over those. It flows over, and that's why I see towards the edges. You see, for me to believe Maxlow, what I would have liked to have seen was a smooth gradation of the ages from, say, 280 million where the continents are going all the way back to the mid-ocean ridges. But because I see a series of bands, I think it's evidence of sudden events and a washing over material. So this is why I disagree with the
observation,
Yeah. This is why I disagree, and I go to my own laws of proportion, and I believe in my own Earth expansion theory. So that's why I'm putting all that out there, because what I'd like to do now is to go on to discuss some of the issues of gravity and of the dinosaurs.
Good, great.
Yeah.
Go on,
So, but I needed to tell you why I think I disagree massively with Maxwell's theory, and I believe that a major issue is the distribution of mass within the Earth, but I think the Earth's size has not changed much over the past 250 million years. So the dinosaur issue, actually, I've got a book here which is all about gravity. This book's quite old, and it points out, again, probably the same studies that you've looked at. We have here a dinosaur image, and again, we've got this reference to, I think Science Magazine, 1984, and then other studies. It basically says here, at the time of the dinosaurs, the gravity acceleration on Earth would have to have been 25 to 30% of the present day acceleration. And they look at anatomy, of saurian anatomy, and things like that. And again, pterodactyls, they can't even get off the ground, they'd not be able to fly. So the issue is then, how do we get lower gravity going back in time? And this has a bearing then. So let's talk about gravity now. I am going to cite a few things here, going back. Richard Hall? He did an interview.
Roger Anderton.
Yeah, the one about Boscovich. You know the one?
Yes, I do. I've read quite a bit about that, actually,
Very interesting one. I'm going to really add to that. You'll find
great.
But gravity-wise, most people today think general relativity is the dog's bollocks, basically.
That is true.
And basically, the idea, strange as it sounds, you've got this thing called matter stuff, and it's embedded in space-time, and you can try and visualize that one. It's embedded in the fabric of this space, and with its presence, it creates a condition which causes it to expand or depth. You've seen the images of the balls on the mattress. It creates curvature in space-time going away. And this is the general theory. Now, interestingly enough, there was a really prominent critic of general relativity who really thought it was a load of bollocks. And that man is Nikola Tesla. And he had quite some objections to it. And he actually cited Isaac Newton, to basically condemn relativity theory. He said, look, Newton says quite clearly, for every action, there's an equal and opposite reaction. So if you plonk the mass in space and disturb the space outwards, it's only going to come right back at you and re-establish equilibrium. He says that's one of the basic points. But Tesla looked very carefully at the whole thing, and he said it was like a fantastic mathematical pacifist, but it was all nonsense. Yeah, he basically condemned it. But Tesla also, in one of his citations, is recorded as mentioning Boscovich, the work of Boscovich. And Boscovich is a guy who lived in the 18th century, right? I believe it's 1711, I think he was born, something like that. He lived totally within the 18th century. And Boscovich was looking at the work of Galileo and gravity. And this goes back to the interview we just mentioned. Is it Anderson? Roger Anderson?
Yeah, Roger Anderson, yeah.
And the main topic was Boscovich and his theory, which was basically a kind of an atomic theory, but it could hold true also for planets. Because when you think about the 18th century, the conventional view of history is that we didn't even know atoms really existed. Amazingly enough, there's some very interesting digressions you could go off on there, but the idea of atoms, we hadn't really got it. We hadn't a working theory, but we were just thinking that matter must exist in some kind of particulate form, really small level, but we didn't really know anything more than that. So Boscovich was he was looking at this idea of forces around matter. And it was Niels Bohr who worked upon Boscovich's theory from an atomic level to come out with his theory of electrons orbiting an atomic nucleus. So if you bring up image 18 here, this diagram I've kind of ripped off from Richard Hall's, it's a snapshot from his presentation with Anderson. And they're talking about Boscovich's, and Richard explained this quite well. It's a force distance diagram. If you imagine an object located at a point on the line of AB, where the big thing goes up, imagine an object there, and this is a distance moving away from it, and you can see the ripples, right? The distance is the x-axis horizontal. The force is with the y-axis. And so basically what it's saying is, as you move away from an object, you can at one point get a force increase, and then it reverses and then starts to decrease, and then it goes back on the increase, and it's doing this. It's creating these kind of repulsion attraction things going through it, yeah?
Okay.
Now, this was very interesting to me in looking at it because of what is in my own book, basically. As I said to you, I have not just studied the Earth and the Moon. I studied all the planets. I very carefully looked at all their semi-major axis values expressed in units of 6,000 feet, the ideal geographical miles, and looked at their orbital periods. And I worked out that there's been a general transformation of the solar system. When I was being interviewed by Richard Hall, he asked me about this. And I have to say, at that time, about 4 years ago, the explanation I give was not very great, and I've modified it dramatically since then, and I believe I've kind of got it nailed. But what I found was a strange sort of reversal that you might not expect in the solar system. And basically, it's to this effect. If we take the sun, and you look at all the planets orbiting the sun, as a general rule, right, the further away you are from the sun, the longer it takes to orbit. But look at the moon. Look at the moon orbiting the Earth. The data I've just given does our own observations say of the moon. They say currently the moon is increasing its distance from the Earth. It's moving away. But what does the synodic period data show? It's getting less and less time to orbit it, yeah? It takes less time to orbit it. So as it moves further and further away, it'll be going round the Earth even faster. You would not expect that. You would expect it to take longer to orbit as it moves away. Yeah. What I found in looking at the planets is the same thing. For example, the planet Venus, its orbital period is about 224.695 in terms of its days, days to orbit. Ideally, it was 225 exactly. It's decreased its orbital period. Yet, I find very powerful evidence that it has increased its distance from the sun at the same time. And I would even say the rate of increase is the exact same ratio as between the current tropical year and an ideal of 360. It's the very same ratio, that 1.01456. As powerful evidence I present for that effect. So I show that some of the planets are moving away from the Earth, and they're also increasing their
distance. Others are moving away but decreasing their distance. And what this basically is confirming the same thing Boscovich was essentially saying. So if you imagine then that you have, if you're a certain distance from the sun, you're in orbit around it, and you just keep extending the orbit away, you may initially find that, oh yes, as your orbit's extending, the time taken to go around the sun is increasing, but then you'll find it suddenly reverses, it'll stop, and then as you keep on going out, it'll take less and less time, and then that will reverse. And I find in my own research that is exactly what we have with the solar system and the planets. Yeah, that's what's going on with the planets. And Boscovich here is saying that's what's going on at the atomic level. Yes. And Niels Bohr as basically, because he sees this repulsion attraction, he sees these key orbital radius values of the electron, and he's saying, Bohr's saying, you have to be at these intervals, and if you want to move to another one, you've got to have just the right energy inputted to give you the jump to the next level. And if it's not enough, you can't get out, you're trapped. So what I looked at then, I looked at this, and this led me to the work of Stan Deyo. Yes. Now, Stan Deyo, there's a presentation on the internet, and I've got it. It's a very, very important presentation. And this is something, if you've not seen it, it directly ties in to what you've been doing and what Peter Woodhead's been doing with the gravity. Okay. And Stan Deyo, he had one of these above top secret clearances, worked on black budget projects, especially in Pine Gap in Australia, right? And so he's a bit of an insider. He knows some stuff. And he also says that, he worked on, he's associated with Edward Teller, and they worked on anti-gravity propulsion systems. And these propulsion systems were based upon an understanding of gravity itself as a field. Now, the idea of gravity, at least conventionally under, say, Newton, was it's all an attraction phenomena. What Boscovich is showing is we've got this attraction repulsion thing, right? And this has been extended to the atomic realm by Bohr, right? Mm-hmm. Now, Stan Deyo in his presentation says something absolutely amazing. And when I saw this, it nailed it. Basically, he says that the planets have their orbital bands. They are established by a certain process. He said the sun, at the center of the solar system, it's spinning around really, really fast, and it is pushing space outwards. It's expanding away. So if it's spinning around fast, you're going to have like spiraling centrifugal waves going outwards. Okay. But the critical point, he said, space has resistance. Imagine you've got a sponge, you've got a wall, and you've got a big block sponge, certain density. You push against it, getting it denser and denser and denser, and then you release it, springs back. If space has resistance, these waves will expand to a certain limit. And when they reach that limit, they then spiral back inwards centripetally. And the outgoing waves meet the incoming waves, and what do you get? A series of established standing wave patterns.
That's what you're saying.
And these will have embedded in them the gradients of the pressure of space itself. Pressure gradients in space, And the planets have to be located inside these pressure gradient troughs, if you will, right? This is what Stan Deyo was saying. And this is critical. But not just the sun creates these waves. All celestial bodies do. The Earth, the Moon, everything. And although Stan Deyo says the sun's spinning around really fast, it's not the physical outward form of the Earth which is generating these waves. It is far higher, faster rotational speeds, I would say vastly in excess of the speed of light, near the core, which are creating these pressure waves and establishing the return signals and the harmonics. Now, this is kind of critical then, because here's the key thing. If you've got the, in physics, we've got the general inverse square law for gravity, Well, what this means is, if the general inverse square law, the ratio, or the ratio, if you will, between the, let's say you've got an expanding sphere, it'll have a radius and it'll have a surface area. if the radius is increasing, the sphere, if you imagine it's getting thinner and thinner and thinner, its density decreasing, yeah? The ratio there follows an inverse square law, and it's like a mathematical desire, if you will, to push space to infinite density, because even though your sphere is getting less and less dense, you imagine you're pushing space outward, it's getting more and more dense in that sense. So you're space to infinite density at infinite distance, yeah? And that general inverse square, the reason why it goes on forever is for that reason. But the reality is, celestial bodies only have the power to push space as to the limits of the resistance of space, based upon the power itself. So you won't get a perfect inverse square law modeling here. But here's the thing. When you get these return signal waves coming inwards and you establish the gradients of a standing wave pattern, much like in Boskovich's diagram, right, what you will find is that a general inverse square law will connect up gravity acceleration at the troughs, the successive troughs, within the wave patterns, yeah? So if you jump from one planet to another, the centripetal acceleration, gravity towards the sun, say, if you jump from where Venus is to the Earth, yeah, and you jump from the Earth to Mars, you'll think that inverse square law is brilliant. You'll think, yes, because it connects up the troughs. But the key thing is, the gravity acceleration wave between planets, if you move between them, diverges from the inverse square law and goes in accordance with the ripples of the pressure waves of these harmonics, which are the superimpositioned waveforms. Yeah, this is why gravity and the inverse square law is so deceptive, because you see, you've got your observations of the planets and you think, yes, the inverse square law, gravity acceleration must be modeled flowing all the way between the planets according to that curvature, but it doesn't. It only works if you jump between planets, because they're all in these gravity troughs and the pressure waves are the same there, so they're linked by it. But the gravity acceleration waves between them will diverge significantly. And this brings me on to my last couple of diagrams. Image number 19. What you've got here then is the Earth itself, which is emitting its own pressure waves in space, which is giving a return signal. And the Earth sits in its own established gravity well, if you will, right? And you can see the curvature here, best as I can do it, the curvature of the inverse square law acceleration values from the Earth center to the Moon follows like so. But what I suggest is that the true gravity acceleration actually goes via the pressure waves, as you can see, the superpositioned waveforms, and the force reversal points are right on the, if you will, the peaks of that, yeah? And the material body of the Moon, it's stuck in its own wave that the Earth has generated. So an inverse square law, because it connects up the center of the Earth, to the Moon, and because the surface of the Earth is very close to that there, gravity acceleration will appear deceptively, tantalizingly, to follow a general inverse square law. But what you find as you move further away towards the Moon is the divergence gets bigger and bigger and bigger, right? Now, I show here, this is the ideal system. And I now cite the work of one Walter Russell, whose book, Atomic Suicide. He talks about the very same thing, about how bodies are formed by centripetal waveforms spiraling inwards to compress space, and they are unraveled by centrifugal forces going off the equator. So he also says that you achieve maturity of an object and perfect balance in a single gravity axis when you achieve a spherical state. And he even cites carbon as the atom which has this spherical state in its ideal form. And incidentally, the melting point of carbon in the form of diamond is the highest melting point of all the elements. And its melting point, Russell cites here, 3,600 degrees. This gives you the connection to the Earth's own orbital period. Now, interestingly enough, if you go back to the Sumerians, you can cite the work. Sitchin cites this, Zechariah Sitchin, because he looks at this number 3600. He thinks it's to do with Nibiru, you know, and basically he holds it to be a very eccentric orbit. But I'd discard that. He gives you a few references to this number 3600, and it says it means perfect circle or a completed cycle, a princely or royal number. So it's associated with circular or even spherical or a maturity in nature. Yeah. Now, if you take 3600 degrees, though, if you look in the textbooks as to what the melting point of carbon is, it won't tell you it's 3600. It'll say 3550, yeah, 3550, right? Now, if you have 3600 then as a value and you divide it by the ratio of the Earth tropical year, you get 354.5. So I would suggest that carbon as atom and all the thresholds of the melting points in the periodic table, they have subtly shifted just like planets themselves in orbit, yeah? And so what I see then is the Earth's a perfect sphere. It's almost a giant carbon atom, so to speak, in a macroscopic world, all right? And it's not rotating. And this is what Russell says. Once you achieve the ideal state, the spherical state, rotation at that point is a cessation motion. You've completed the centripetal spiraling inwards. Now you go into a centrifugal curve, so you have a switch around. You've completed that cycle, yeah? But here's the thing. Mass distribution in a spherical Earth, what would it be? Well, if you've got the pressure waves going out and coming back in, right? You know how the pressure waves going out to achieve a kind of, you know, the highest density pressure on the outside of the shell. When they rebound back, they come all the way back in, and you have highest density at the center. So if you look at the actual, in the diagram here, I've got a single gravity well for the Earth itself, yeah? And that would be at the highest gravitational accelerations go right to the center of the Earth. Mass would be concentrated more towards the center of the Earth and be less dense towards the outer edge of it as a spherical body. And I believe at this time then, the gravity acceleration, right, the curvature of that little loop of the well, when it reaches the surface, it will be of a very low type that will satisfy the dinosaurs a couple of 100 million years ago, yeah? And that's the kind of change that we have. Now, if we move on then to image number 20, what happens here, and this is I've tried to do this the best I can in terms of a freehand drawing. What happens is, and this is what Russell says in his book, he says, a spherical body, once it's achieved that state, then begins to have more of a discharge principle of its material than a charging principle. So it becomes oblate, it expands at the equator, and a hole is effectively burrowed into it, into the center of it. It develops a hole and it starts expanding outwards, part of the unraveling discharge process. And even says you can find evidence of this by looking at various different nebulae. There's one picture here. He talks about the expansion rate at the equator. So, yeah, and you've got the nebula, the hole's being burrowed right into it, yeah? So that's the kind of unraveling of it. So this is a macroscopic entity revealing what happens even with planets, right? And what that really does, though, mathematically and, well, physically, the rotational forces that expand space outwards are dynamically transformed. And the single gravity well is split into two, right? As a hole is burrowed in. And so what you have then is you've got the outer core shell, like so, you've got a gravity wave, a pressure trough, and the very material of the Earth itself is pushed outwards from its center point where high density was. Because these waves split outwards, the material is distributed in accordance with the shift of the harmonics of these gravity waves, yeah? So it all congregates in a shell, right, with a material. And interestingly enough, Stadio, in his presentation, he actually stated the following. He said, regarding gravity, he gave this very specific example of the Earth right now. He said, look, he said, if you were to drill a hole right from the surface of the Earth right through to the centre, and you were to drop an object down that hole, conventional theory would say it'd fall all the way to the centre. Stan Deyo says it'd fall only a couple of 100 miles down, and then it'd stop and then go up a bit and then fluctuate, and it'd reach a still point. This is the still point here in the detail, where you've got the hollow Earth, that bit there, the superimposed waves, the pressure waves, gives you the still point. But as you can see again, as I try to indicate, the general inverse square law, so that gravity trough, that neutral point, going all the way to the moon. But the connection is only valid jumping between points. The curvature or the acceleration field actually goes via the standing wave patterns, so it diverges. But this only comes apparent the more you move away from the Earth altitude-wise towards the moon. But it's deceptively close. Now, Peter Woodhead was, in the talk you were giving with him, he was talking about various gravity anomalies of mountains like Machu Picchu, I think, and Mine Shaft, and also looking at 1 or 2 satellites in orbit, yeah? And I would suggest that the reason why these things are not quite as they should be is because gravity acceleration, as I said, continuously flowing, right, does not follow an inverse square law. So the gradients will be all slightly off. But in order to model them correctly, you have got to deduce the correct wavelengths of the expanding wave patterns and the correct wavelengths of the incoming patterns and superimpositioned waveforms in order to work out the gravity acceleration values. You cannot use an inverse square law. It will be wrong. But it's tantalizingly close to the surface, enough to make you think that, you know, it follows it, and that's what would resolve those issues. So
also, I mean, you know, obviously you can finish off in a minute, but we've had some other research done, or well, not so much research, but another theoretical paper has been written by somebody else, which I think explains some of this, and that was posted on my website about a couple of months ago now, so it's quite recent. So yeah, maybe we can talk about it. But yeah, carry on with the way where you were going.
Yeah, and this is one of the things I want to just tie this into something else a bit. You see how I've done this as best I can. We have this forced reversal effect as you go towards the moon. This would mean that the journey time to the moon should be significantly different from the orthodox value of about 3 days. Probably even half that, I would imagine. And it just made me to think about a book here. Anti-gravity book here. It's several chapters written by different people, and there's one here, and the guy's talking about the whole issue of the moon landings. And he basically cites a lot of these probes sent up in the 1960s, like the American Ranger space probes, and how, you know, they were either flying by the moon, completely missing it, or smashing into speed when in fact, you know, they were supposed to be doing a soft landing. And same with the Soviets. And he mentions a few of the different ones in the 60s. And I think that this is all due to the curvature of gravity being different and a forced reversal effect kicking in. A strong one from the Earth itself. And this is the moon's gravity. But the moon will have its own similar superposition waveforms, but they'll be a lot weaker than the Earth. Yeah, it will have its own, but I think the dominant ones are from the Earth. And I think this is why some of these discrepancies here. And he even says the Soviets were intensely secretive about the data they collected. So when all the the Americans and the Russians were realizing that it wasn't playing out as much as it should, they didn't want to share this data. So I think they realized the gravity acceleration wasn't the same. And the journey time was different, and they didn't want to release this. And one of the reasons he points to, if you can understand that there are these force reversal effects going on, this plays into being able to develop anti-gravitational propulsion systems. But if you believe that gravity is purely an inward attraction thing, you'll never make those breakthroughs. So this is why very much classified the whole issue of gravity, because of what the implications are. So I think that's about it, really, unless you've got any further questions.
Yeah, I think I've really only got, it's very interesting, Keith, and thank you very much for spending time both talking to me and putting the slides together that I have, which I'll put into a video for you and for us, and I'll send you a link. I did have just one question which I was thinking about while you were explaining, while we were talking about the seafloor expansion and so forth, and what I can sort of follow was how continents actually fitted together words, because okay, Maxlow realized seafloor expansion rates and stuff, but it seems pretty clear to me that the continents do actually fit together. So this overall idea that there wasn't an ocean floor one time in the history of the Earth, and now there is, that seems to me to be quite valid. I don't know if you had any thoughts on that.
Just to clear that, I've seen estimations. Is it by Neil Adams? Yeah.
Neil Adams there are other people that have done the same thing, because Max done his own, and so has somebody didn't mention, which is Stephen Hurrell. He also did a thing where he just literally removed what was the seafloor, areas progressively, and then shrunk the globe back.
I agree with that. I do believe that we did have Pangaea and the continents locked together exactly like they said, and the Earth was roughly half the size. But I believe that was billions of years ago, not 250 million. And what I kind of see it as is this. We had Pangaea like that, half the size, and we had purely continental crust, but that was sat on top of another layer. And what's happened is this other layer has expanded, cracked the continent, and it's continued to expand, and the continental material is just sat on top of that, so it's expanded and moved around and got into position as it is right now, and it's an inner layer.
So the underlying sort of situation of a smaller radius globe, you're sort of fairly happy with that idea, and it's just in terms of we've Maxlow and both myself and Peter, we've sort of put forward the idea that there was no expansion for 3 billion years, and then it was about 300 million years ago the expansion actually became exponential. So I think in that regard, the difference that we've sort of considered is the movement, the way that things have moved about, and the rate at which that movement has occurred. I think those are the only things that I think I was particularly impressed with the 0.2 millimeter figures that you sort of worked out, and then looked in the literature and so forth. That was very, very interesting. And as regards the dinosaurs, then you think the gravity changes have occurred because of these changes in the gravitational waves. Is that correct?
Yes, it's a transformation of those waves. You see, that's the key thing. It's like you've got these superposition waveforms created by the Earth itself through the speeds of the inner core, right? And when the Earth becomes hollow, as it loses its spherical state, they shift, and the material shell, the matter of the shell itself, is locked into one of these gravity wave troughs, just in the identical way as the moon is. And so if you go from that little trough, weird inverse square law, you'll seem to model gravity very close to it initially, but it doesn't really follow.
And so you mentioned things oscillating, or maybe oscillating is the wrong word, but you mentioned something changing faster than the speed of light.
Oh yes.
Inside. So my obvious question then was, what would be the source of that sort of change within a planet or within the sun, or do you have any thoughts on that?
You've got a video of somebody discussing electric universe theory embedded into one of your web pages, and this guy was talking about the orbits, I believe, of electrons around atoms. I just looked at this, and he basically said that I think he was referencing somebody else who'd done some calculation to say that they have to be orbiting multiple times the speed of light. Now, I believe that solar systems, obviously, are like macroscopic versions of atoms, Okay,
and that's essentially what Boscovich does.
Now, really, I don't believe in the speed of light being the maximum limit. I think that's nonsense. The black hole theory as well, I dispute that. What I would say is, just as a general point, and I did a calculation, I hope I got these right because I did this just last night, but I took the gravity acceleration rate of the Earth right at the surface, and I took it down to the radius of the Bohr radius of the electron orbiting nucleus hydrogen atom.
Okay.
And I just worked out what the acceleration value was really, really close there. And once you've got that acceleration value, yeah, and once you've got the radius, velocity squared, divided by radius is acceleration. So if you've got the acceleration value, you multiply by radius squared, square root it. Just imagine what the acceleration speeds would be, and I got a value something like 10 times the speed of light. And I did the same thing for the sun. I don't know whether I've got it here. If I've got this right here. I did the same thing for the sun. And if I got this right, it was something like 5.2 million times the speed of light if I did it for the sun. Okay. So what I'm saying is that I believe the planet Earth is effectively a macroscopic entity engaged in radioactive decay. Follows the theories of Russell here, yeah? So what I think, you've got rotational forces massively in excess of the speed of light. These forces which establish and give you the pressure waves of space, the gradients, and because they're operating higher than the speed of light, this is why our technical equipment, can't interact with the gravity field. We can't perturb it. We can't, detect, interfere with it. And what I think is going on is these higher rotational forces are slowing down by, intervals within the Earth, and they slow down by increments, giving off pulses of energy, pulses of speed, if you will, of just less than the speed of light. And this gives you like beta radiation, gamma, alpha, and this is particulate stuff. So what I think is going off is the shell of the Earth is being built up and increasing its mass by these rotational speeds just slowing down and throwing off material, so it almost appear to be emerging from nowhere, if you will. But it'll be all a result of these higher speeds slowing down, converting. It's like, for the sake of argument, if you had an object going at 10 times the speed of light orbiting around the core and it dropped to 9 times, you could have a gamma ray burst, give off by that atom, because that travels at the speed of light. Or if it was less than that, it could be a particle of a beta or alpha radiation. So I believe that that's basically how the Earth is building up mass. I believe the Earth right now has stored in it essentially enough material to make it a gas giant. It's just in the process of discharging that through macroscopic radioactive decay, which is going to be building up to its a higher size. So I think there is a mass expansion along with a size expansion, but both have occurred very subtly. For me, I do believe, as I said, we had Pangea a couple of billion years or so ago, right? And that the splitting up there is, as you say, the Earth was once half the size. Don't get me wrong, it was. But about 250 million years ago, I think we'd already lost Pangea then. We'd already lost it. We had the continents dotted around, and they were sat on top of an inner layer, which was lower down. And it's that inner layer that cracked, and the material flowed out within that well. And that's where I think has created these seafloor bands. I'm more confident in the interpretation of Pangea and Earth half the time, 250 million years ago, if there was a smooth gradation of the aging. But because it's bands, and because of Van Vanden's theory, I think it's shock waves that give us it.
Yeah. All right then, Keith. Well, thank you very much for spending the time, and it's been very, very interesting. I've learned quite a lot, which is always good. And so we'll put this out, and we'll see where it goes.
I'll send you the links as well for some of the articles, so you can put them on your article.
That'd be brilliant. Yeah, I put those at the bottom then, and people can follow that up as they wish. Okay,
thanks for having me.
You're welcome. And just to give people your website again, I assume you've got a website.
Oh, yeah. My website is occultphysics.com, and it's all one word, no space. Occultphysics.com.
Okay, thank you.
And the book, unfortunately, I've run out of physical copies, so I don't sell it anymore. But I'm working on a new edition with new discoveries, so that hopefully might be out in. It might be out in about 6 months. So if anybody likes my website, if you want to because I self-published, so I'll only do a small print run again. Yes. If anybody wants to reserve a copy, by all means email me and just tell me, and I'll put your names in a list. And the minute I've got them manufactured, I'll contact you first off if anybody wants to do that. Okay.
Okay, then, Keith.
Okay,
again,
then.
Thanks very much, and yeah, great to talk to you. And thanks again.